Okay, all right, welcome to class 8. So, if you remember in the last class we stopped at a point where we said, understanding symmetry of the material is important to predict its properties without even understanding so much about the physics of or the origin of each of these properties. And we looked at examples of piezoelectric tensor just becoming 0 or any third rank tensor for that matter, even second harmonic generation tensor just becoming 0 if I impose the condition that my crystal has an inversion symmetry, right. Just to recap, or just to I made a small mistake last time when I was explaining you about the stress and strain tensors, especially the strain tensor, which I was trying to define the deformation tensor as the displacement, the differential of displacement with respect to the coordinates, right. So, this is delta L by L sort of an equation, but it is a tensor in 2 dimensions. And then I said a part of this deformation tensor is what is given as delta, and delta is nothing but the so it's I said this delta just comes out of rigid body rotation. I don't need to deform anything. If I just rotate my object, the deformation, the ensuing deformation tensor, which is so of this nature is nothing but 0 minus delta u2 by delta x1, delta u2 by delta x1 and 0, right. But instead of calling it a part of deformation tensor, what I said was it is a transformation matrix, right. So, today let me first correct that. This is not transformation matrix, right. So, I am not transforming my q1 to q2, rather what I am just writing as delta is just a part of the deformation tensor, right. So, the deformation tensor is defined as E is just dou u1 by dou x1, dou u2 by dou x1, dou u1 by dou x2 and dou u2 by dou x2, right. So, this delta when there is just rigid body rotation is given as 0 minus phi and 0, where phi is the angle of rotation, and that can be just shown through this simple rotation of a rigid body. Okay. So, that is what I showed, but I represented this as a transformation matrix. It is not a transformation matrix. I am not transforming one coordinate system into another coordinate system. It is just part of what is the deformation tensor, right. So, I will just write it as what is, instead of saying what is the transformation matrix, I am going to correct it as what is the deformation tensor for a rigid body rotation, and that deformation tensor is not 0, right. Ideally you want the deformation tensor to be 0 if I am just rotating, but it is not 0, it is actually this delta which is an antisymmetric tensor. So, from the total deformation tensor I remove the antisymmetric part and just say that strain is the remaining symmetric part. Okay. So, I hope so that clarifies the mistake I have done in the last class. I apologize for it, but here I have corrected it. Okay. So, with that let us move on to symmetry. Right. So, structure and symmetry. So, what so I can probably impress upon you the idea of symmetry through these objects, right. So, let us first look at all these objects. So, for example, if I see all these objects, there is some kind of symmetry involved in all these objects, and all these symmetries are nothing but some form of rotation symmetry. For example, if I am here, right. So, I rotate this object by 120 degrees, right. So, that is 3-fold rotation. If I do a 3-fold rotation about this point, which is the centroid of this triangle, I exactly get the same object, right. So, there is going to be no difference, right. Similarly, here there is a 5-fold rotation axis. The point that I am pointing out, the centroid of this object, the star, is a 5-fold rotation axis, and if I rotate this by 5-fold, that is 360 by 5, then so I get the same object again, right. So, here I have a 4-fold object of rotation, here this is 6-fold and so on and so forth. So, you see all these flowers etc. in nature are all they have so there is a lot of symmetry in nature, and one of the symmetries that we see always is a rotational symmetry. Okay. So, we will discuss what rotational symmetry is, but so understanding the symmetry will try so understanding symmetry will ease our understanding of crystal structure, right. So, and how to represent crystals by the symmetries that are present in the crystals. Okay. Then so if I go next, okay, so next. So, I am going to define this is one of our dogs in IAC that sleeps every morning in our gymkhana, right. Now, this is such a unit, right. So, I am going to call this an asymmetric unit, right, and I am going to ask you the question. It has its own, this dog has its twin brother, right. So, every morning you go, you see that the dog and its twin brother are sleeping in front of a door, right. So, that I am going to show you later. If I show you some such image, right, so with no background, nothing, right, you are going to say that okay, these both look alike, there is some form of symmetry here, maybe a mirror plane here, right. So, there is going to be some sort of mirror symmetry here, except that when I put it in conjunction with where exactly it is sleeping, the background, the surroundings, right. So, the mirror is gone. Okay. So, this is what is going to happen. I am going to put some asymmetric units in an environment and then see what are the asymmetric units can be atoms, bunch of atoms or any sort of motif. I am going to define all these terms later, but I am going to put this in some sort of an environment and then see if there are certain symmetry elements that come up. Right. So, if I put these two dogs in this environment that I showed, there is a mirror plane here, right. So, you can sort of see that there is some sort of mirror symmetry, right. So, these are actually different dogs. So, if you see very carefully, maybe there is no mirror, but so on overall I can so at least predict or at least intelligently think that intuitively say that there is some sort of a mirror plane, right. So, here if I show you this environment, there is no mirror plane, the mirror is gone. Okay. So, we are going to look at these sort of operations and let us go back. We are going to look at these sort of operations, and initially what we are going to look at is we are going to look at what are called point symmetry operations. Right. Now, what is point symmetry? Point symmetry is symmetry about a fixed point in space, right. So, about that fixed point I am going to rotate, I am going to pass a mirror plane, I am going to do something, right. I am going to do some sort of symmetry operation such that that point does not change when I am doing any sort of symmetry operations, right. So, these are symmetry operations about a fixed point. Right. So, these are what are called point symmetry operations. Not to confuse this with point groups that I am going to talk about later on. So, these are just called point symmetry operations. Okay. Now, what are the various point symmetry operations? So, we can rotate about a point, just like I was showing you all these various sort of rotation symmetries, objects with several rotation symmetries, right. So, I can do what is called a one-fold rotation. Right. So, this I am going to represent it as 1, right. So, this is just an identity. If I have a point x, y, z in space, if I do a one-fold rotation, right. So, I am going to go back to the same point x, y, z in space, right. So, this is sort of what is called an identity operation or okay. So, I am going to have I am going to describe two different notations. So, one-fold rotation is just called 1 in the IUPAC notation, right. So, this is international crystallography notation, sorry, it is not called IUPAC, it is called ITA. Tables of crystallography A, right. So, ITA is volume A. Okay. So, this is the notation. In the ITA notation I am just going to call one-fold rotation as 1, right, of a vector, right. So, one fold rotation about a point of a vector. I am going to call, so there is another notation that mostly molecular chemists use, this is called Schoenflies notation. Okay. So, in the Schoenflies notation, this is just an identity operation which is called E. Okay. So, I am going to write it as 1 or E, right. So, this is the ITA notation, this is Schoenflies notation, all right. So, what is the, there is for every, this is an operation, this is a symmetry operation, or so what is a symmetry operation? I transform a vector x y z to what the symmetry operation takes, right. So, symmetry operation is a matrix essentially A I J, it is a transformation matrix. In this case transformation matrix is nothing but the identity matrix, but since it is a symmetry operation, when I transform by this matrix I should exactly get the same point, or I should exactly get the the same point in a similar environment, etc. I should not be able to distinguish the environments of this point or that point, right. So, that's what is meant by symmetry. Okay. So, the simplest form of symmetry operation is one fold rotation, all right. Let us go to the next complex one, which is nothing but the two fold rotation, right. So, next you have two fold rotation. Two fold rotation in ITA convention is just written as 2, and in Schoenflies notation is written as C2, C for circle or rotation and 2 is two fold rotation. Okay. So, what does it mean? So, I am going to draw these sort of what are called stereograms. I will explain you more about stereographic projections later on, but for now so if I have an axis, this axis is let us say a 0 0 1 axis. So, then I say that there is two fold rotation about 0 0 1 axis. Okay. So, now this is the axis is coming out of plane and this is the 0 0 1 axis. I am going to denote it as something like this, right, an oval, right, and I am going to say that there is an asymmetric unit, the dog that I described, right. So, that is an asymmetric unit. If there is an asymmetric unit here, right, because of two fold rotation I should also have the same asymmetric unit here, right. So, when I rotate it by 180 degrees, okay, so it does not look like I rotated it by 180 degrees, but you can imagine that that is the case. Okay. So, if there is an asymmetric unit here, the same asymmetric unit should be here, right. So, this is the complete stereogram. So, again if I rotate this again by two fold, so here I rotate this by 180 degrees, I have an object here, the same asymmetric object. If I rotate it again by 180 degrees, it comes back to its original position, right. So, this is how I represent a two fold rotation, right. So, this is 2 0 0 1. So, what is the matrix, right. So, Aij for a two fold rotation or 2 0 0 1. The matrix of rotation is nothing but so if I have, if this is x y z, right, I am rotating about the z axis or the c axis, this will be minus x minus y z, right. So, based on this you can write the matrix minus 1 1 0 0 0 0 0 0, x is transformed to minus x, y is transformed to minus y, z is just remains, right. So, z does not transform. Okay. So, so this is what is called a two fold rotation. Now, I can also rotate, I can also have a two fold rotation about 1 0 0, that is so I have, this is my axis of rotation, right. So, this is the 1 0 0 direction, and if I have an object here, right, so which is coming out of plane. So, if it is coming, if the object is coming out of plane, I am going to call it plus, right, in this asymmetric object. And if I do a two fold rotation about z axis, about the c axis, the out of sorry, if this is coming out of plane, this object also will come out of plane, right. So, the plus remains, whereas in case of if I am doing a two fold rotation about this axis, let us say, right. So, that axis I am going to represent here, this is the 1 0 0 axis, right. If I have an object here which is plus, which is coming out, then the two fold rotation takes it down, so it is going to become minus. Okay. So, that is simple, and the matrix for 1 0 0 will be 1 0 0. It is just the other the y and z, right. So, those diagonal elements become minus 1, right. So, if I have x y z is actually transformed to x minus y minus z, right. So, that is what a two-fold rotation does. Okay. And in Schoenflies notation, two-fold rotation is typically you see this thing called C2. C2 means I have a two-fold rotation in my molecule or in my entity about a point, right, and this two-fold rotation so molecular chemists typically use the Schoenflies notation, right. Okay. All right. So, next we are going to talk about three-fold rotation, and so three-fold notation I am just going to represent it again using these stereograms as a triangle at the center, right, and then I am going to have these things at 120 degrees with respect to each other. Yeah, so and this one. Okay. So, now if I have an object which is here, let us say, and it is coming out of the board, out of the plane of this paper, then I will have another object which is rotated at 120 degrees. I will have another object which is rotated at 120 degrees, and so if I rotate this back by 120 degrees, I get the same object. So, this is the symmetry operation. If I have an object here, I have an object here, I have an object here, right. So, that is the three-fold rotation, okay, which is represented as this, right. So, I mean, since it is a stereogram, I am going to draw it on a circle. Okay. I mean, so you will see that this is some sort of a stereographic projection of a three-dimensional nature, but so for now it is I can just draw circles and then represent these asymmetric objects, and these asymmetric objects are rotated by 120 degrees with respect to each other. So, what is the rotation angle? Rotation angle is 2 pi by 3 is my theta or rotation angle, right. And if I have such an object which is three-fold rotated, I call it I call that I have a point symmetry operation which is three-fold rotation about that point. Okay. All right. So, then the next thing is four-fold rotation. Right. And four-fold rotation, so the way I represent it is as follows, or I can also have diamonds representing the four-fold rotation, right. So, I have this axis here, this axis here. If I have an object which is here and this object is pointing up, so I have a 90 degree rotation, right. So, that comes here, sorry, and then the same object should also exist here, and the same object should also exist here, right. So, this is the four-fold rotation, a stereogram for four-fold rotation. Okay. So, or in other words, so if I do 1 4 rotation, I come from here to here. If I do 2 4 rotations, I take this object from here to here. So, 2 4 2 is exactly the same as two-fold rotation, right. So, 4 2 is the same as this operation, this symmetry operation is the same as two-fold rotation. If I do 3 4-fold rotations, it is equivalent to going 90 degrees in the clockwise direction, right. So, instead of going 390 degrees in the anti-clockwise, you go 190 degrees in the clockwise direction, 4 3, right. So, and 4 4 is again your identity, or you come back is equal to 1, right. So, you come back to the same position again. Okay. So, that is a four-fold rotation. And next what I am going to talk about is not 5-fold rotation, because I am going to I will tell you why I do not really care much about 5-fold rotations and 10-fold rotations and 8-fold rotations in this course. So, I am going to talk about a 6-fold rotation. Okay. A 6-fold rotation, I am just going to represent it by a hexagon at the center of my stereogram. something like this. Right. And with respect to that, if I have a point here, so let me actually draw. Sorry. Yeah. So if I have a point here, I should have a point again at 60 degrees, again at 100 and sorry, it forms a hexagon essentially. Right. If I have an asymmetric unit here, I rotate this asymmetric unit by 60 degrees and I have it here, and from here again at 60 degrees I have another asymmetric unit which is somewhere here, which is somewhere here, which is somewhere here, and which is somewhere here, right. So I form so this so there is a 6-fold rotation axis. That is my 6-fold rotation axis, right. The center of this is a rotation axis, right. So about which I have a 6-fold rotation, right, in this system. Okay. Now, as you can see, rotations, although I call them as point symmetry operations, all the rotations are being performed about a line. About an axis or a line. Okay. So, technically speaking, so although they are, it is not that a point is fixed, it is I can do this operation anywhere about the line, right. So these are actually line symmetry operations, or so they still classify as point symmetry operations. Okay. But so there is no unique fixed point, it is you are doing all these operations about any point on the axis. Okay. So that is 6-fold rotation. All right. So now why not 5-fold rotation? Why do we not talk about 5-fold rotations, right? So, as you will see in the later part of the course, we are going to talk about, or from next class onwards at the maximum, we are going to talk about crystals, and these crystals have what is called translation symmetry. Right, that comes because of periodicity in the crystal. So, if I have some what is called a lattice point, I am going to define what lattice is later. Here I am going to periodically put the same lattice points, right. So this is what is a lattice, right. So there is going to be a translational symmetry, or if I have an object at x, y, z, I should have the same object at x plus u, y plus v, z plus w, and this u, v, w, and similarly x plus 2u, y plus x plus n 1 u, y plus n 1 n 2 v, z plus n 3 w, right. So these vectors u, v, w are the translation vectors, these are what are called lattice translation vectors. And what you have is actually a translation symmetry in any crystal, translation symmetry. Now, if you have translation symmetry, you can easily show, and I leave the proof to you to show it, that the only point group, the only point symmetry operations that are compatible with translation symmetry, or in other words that can fill space completely, are 1 fold, 2 fold, 3 fold, 4 fold and 6 fold rotations and their derivatives. We will see what their derivatives are, but only let us say point only rotation operations, point symmetry rotation operations that are compatible with translation symmetry are 1 fold, 2 fold, 3 fold, 4 fold and 6 fold. You can actually see that, right. So the way to prove it is, so I have 2 points which have a separation of A, right. So this is a lattice translation vector, right. So this is a lattice vector. Now if I say that this crystal has an n fold symmetry, right. So I take this vector and I can rotate this by 2 pi by n in this fashion, and I can also rotate it by 2 pi by n so in the other fashion, right. So if I rotate it by 2 pi by n, I should get another lattice point. Essentially that is what is meant by saying that, okay, so I have a point symmetry operation here which says I can rotate any vector by 2 pi by n and I should get the same environment, same vector again. So I take this vector and I rotate it by 2 pi by n. So I should get this vector, but so the whatever is here should be here, right. So the environment about this point should be the same as the environment about this point. So this should be a lattice point to be so most basic thing is that this should be a lattice point. If this is a lattice point, this is a lattice point. Similarly, if this is a lattice point and I rotate about this point, this should also be a lattice point, right. Now I can look at what is the length of this, right. So if this is a lattice point and this is a lattice point, the length of this should be some integral multiple of a, n times a, right. So where n is an integral multiple of a. Or since I am using n for rotation, let me call it m times a, not n times a. Where m is an integral multiple, is an integer, not integral multiple. And you can show that this is only possible if m will be an integer only if n equal to, this is only possible if n equal to 1, 2, 3, 4 or 6. Okay. In other words, so if I have hexagon, yes, that is the way to draw it. Go home and so look at what is the structure of graphene, for example, right. So you will see that there are all these carbon atoms sitting at the corners of these hexagons, right. So you can actually fill the entire space with hexagons, entire space without leaving gaps. Okay. So 100% fill factor, right. So there is no compromise. With hexagons you can fill the entire space. So if you have hexagonal tiles on your floor, you can see that the entire floor can be just filled with these hexagonal tiles. Okay. Whereas if you have even if you have square like tiles, so this is akin to having 6 fold symmetry in two dimensional plane, right. So you can fill the entire plane with hexagons, right. So if you have squares, that is akin to having 4 fold symmetry in a plane, and you can fill the entire the space with square tiles, right. So here also you can fill the entire space. But if you have pentagons, right, you cannot fill space without having some sort of some triangles, or you have to make use of some triangles in between to fill space, right. So you cannot fill complete space just with these pentagonal tiles. In between, so there are some gaps that are left, and those gaps need to be filled with other sort of polygons, right. So which is not a pentagon. And that is what this means. This means that your rotation, your translation symmetry, right, so or filling space, right, is not compatible with 5-fold axis of rotation. Translation symmetry is not compatible with 5-fold axis of symmetry. And here I have to mention that although it is not compatible, that is why we do not talk about it in conventional crystals, right. There are what are called quasi crystals, right. So, this is just an additional detail, we are not going to talk about this in this course, but there are what are called quasi crystals in which so you have people have found 5-fold axis of symmetry, or so other forbidden axis of symmetry, right. So you have to forego translation in certain axis, translational symmetry along certain axes for you to have 5-fold axis of symmetry, but such crystals do exist, and there has been a lot of work that was done on quasi crystals in IISc itself, and so being from IISc myself, I should not just skip that out, right. So I am mentioning that there are examples of what are called quasi crystals which have 5-fold axis of symmetry, but that means that you are breaking translational symmetry in a certain direction, right. Right. So quasi crystals can exist, 5-fold axis of symmetry, etc. There are crystals like that, but they will not be translationally symmetric along certain axes. Okay. But if you want complete periodicity and complete translational symmetry in all the 3 dimensions, you can only have 1 or 2 or 3 or 4 or 6 fold axis of symmetry. As a result, we just discussed that, right. So, in the rest of this course. Okay. Now, so rotation is one simple operation. What about, let us say mirror, or let me start much more simpler. So, we were looking at inversion symmetry on the other day, right. So, the other symmetry operations now from now on we will be talking about. So, one of them is actually inversion symmetry. So, you have 1, 2, 3, 4, 6 fold axis of rotation symmetries, right. So, these are the 5 different point symmetry operations. The other point symmetry operation is what is inversion. Inversion is what takes x y z to minus x minus y minus z, right. So, essentially if I have again inversion is represented as I in Schoenflies notation and as 1 bar in ITA notation, right. So, so from now on if I say 1 bar, I mean that I have inversion symmetry or centrosymmetry. So, okay. Now, I have a point, and about this point if I have inversion symmetry, I am going to say I am going to represent it as a stereogram as follows. Okay, so, inversion symmetry means if I have a point x y z, it goes to minus x minus y minus z. So, this is so a plus goes to minus, right. So, that is okay, that goes to minus x minus y minus. But what else happens when you are actually doing inversion? So, if I have to invert my right hand about this point, right, about this point let us say. So, my right hand is here, I invert it as my left hand here, right. So, it is my right hand, the handedness actually changes, right. So, the right handed coordinate axis become left handed coordinate axis, right. So, and so on and so forth, right. So, the chirality of my object itself will change when I invert the entire object, right. So, now my object is not a single point. So, I am not taking a single point x y z and putting it at minus x minus y minus z, but it is a set of points, set of x y z's become set of minus x minus y minus z's. So, if my set of x y z's are right hand, they will become my left hand, right. About the center of inversion. Okay. So, I am going to represent chirality now as if this is right handed, I am not going to show anything, but if this is left handed, I am going to put a comma inside, right. So, chirality also changes, right. So, right handed chirality I am not going to show anything, left handed chirality I am going to put a comma, right. So, so inversion is easy, it transforms x y z to minus x minus y minus z, but what else is it going to do is it is going to actually invert the chirality of my x y z, right. The other operation that also inverts chirality is a mirror, the other point operation, and if you see, inversion happens about a point, it is not about an axis, right. So, you will have a point of inversion. So, about that point x y z becomes minus x minus y minus z, right. So, it is not unlike rotation, rotation can happen about any point on the axis, but inversion is about a fixed unique point, right. So, this is a fixed point. Right. So, and you can get the center of the point, I mean you can get the point as center of these two things, right. Okay. Now, the other operation that transforms right handedness to left handedness is just a mirror, and that is obvious, right. So, if I have if I have a mirror plane between my right hand and left hand, of course, my right hand actually transforms to a left hand, right. So, and if there is mirror symmetry, that means in my complete surroundings I have both a right handed object and a left handed object, both of them are coexisting with respect to each other, right. So, then I say that I have a mirror symmetry in my material, right. Now, so mirror symmetry is about a plane essentially, but that plane passes through your point, right. So, if this is the plane of interest, so I can have mirror about let us say so this can be my mirror plane. If this is my mirror plane, if I have an object x, y, z which is pointing up and that has a chirality which is right handed, I am going to mirror it to xy is sorry in this case x is so minus x, y and z, right. So, it is still going to be pointing up. So, I am going to, this is my mirror plane, right. So, it is still going to point up, but what I have changed is its chirality. So, I will get a comma in between, right. However, if I have a mirror plane, so this is what is called so this plane is my mirror plane and this plane is perpendicular to my x axis. So, the mirror plane is M100. So, M100 is nothing but minus 1 1 1 0 0 0 0 0 0, right. So, it has transformed x y z to minus x y z, okay. Now, I can also have m about 0 0 1, which is going to be what is called a horizontal mirror. So, M100 is what is called a vertical mirror in Schoenflies notation, sigma v, right. So, this is vertical mirror, right. So, in ITA I call it m, whereas in Schoenflies mirror is represented as sigma, right, and m about 100 is what is called a vertical mirror. So, this mirror is coming vertically up the plane, right. Now, M001, right, so which is this is my 001 axis, right. So, it is actually perpendicular to the 001 axis, which means it is actually parallel to or it is horizontal mirror, right. So, this is what is called as horizontal mirror, sigma h, okay. So, now sigma h, what does it do? It takes a point which is facing up, right, and then I have a mirror that is horizontal. So, that point is going to face down, right. So, there is going to be plus and minus, and so I divide it into 2 and the chirality also changes, right. So, then the way I represent it is I divide it into 2, one side I put a comma, the other side I do not put a comma. So, I have both both plus and minus. So, this is both above, this asymmetric object is both above the plane and below the plane. Above the plane, so if I have a chirality which is right handed, below the plane I have a chirality which is left handed, okay. So, that is how you read these sort of stereograms. That is a horizontal mirror. I can also have diagonal mirrors, right. So, sigma d, which is nothing but m about 110, let us say. So, these are my axes, this is my sorry, here the y changes, this is sorry, what I should have done is this. So, this is my vertical mirror, but it is about the x, no, I am right, x changes, that is correct, okay. This is correct. Okay. So, so I can have an x mirror or a y mirror, but what I can also have is a diagonal mirror. Right. So, if I have a, so this is my x axis, this is my x axis, this is my y axis, my diagonal mirror will be somewhat like this. Right. So, about the 110 planes, right. So, so I can have M110 which is which in you know, so in crystals I can have the 110 planes being the mirror planes, and that in Cohn-Fleece notation is represented as sigma t. Okay. So, with that we will stop here in this class, and we will look at what are called roto inversion operations, starting from roto inversion operations in the next class, and you know, we will build on that. So, we will build how crystal structure comes from these point symmetry operations. Okay. All right. So, see you in the next class.